So let's see one more example of Bayes' theorem, which I want to accompany with some more interpretation of what Bayes' theorem is telling us. So here's an example / application that I find very interesting, which is medical testing. And in particular, here is a, well, to me at least, very surprising idea, which we will give, a sort of formal explanation of. If you test positive for a rare disease, you probably do not have it. So this may seem quite counterintuitive, but not to worry, Bayes' theorem will make everything clear. And I've decided that in order to keep the lectures a little bit more PG-13, there's no need to get too concrete with examples of this. But real examples are very easy to come by if you are interested to get real data and try it for yourself. So let's say, suppose we have a disease which is fairly rare. So let's say occurs in 0.1% of the population. And a test for this disease is 99.8% accurate, which means, so in general, there's a difference between false positives and false negatives, but we're just going to use the same number for both for the purpose of this example. So what we mean by this is 99.8% of uninfected people test negative, and 99.8% of infected people test positive. And the question is, if someone tests positive, well, what is the probability that they're actually infected with the disease? And it may seem slightly counterintuitive at first, because since the test is so accurate, you might think that if someone tests positive, it is highly likely that they have the disease, because the test doesn't lie. It is 99.8% accurate, after all. But what Bayes' theorem tells us is that that kind of thinking is ignoring the fact that the disease is so rare in the first place. So let's quantify this. Let's write down Bayes' theorem. We are asking what is the probability that someone is infected given that they test positive. And Bayes' theorem tells us that this is equal to probability of a positive test given that they're infected times the probability that they're infected divided by the total probability of a positive test. So, to introduce some more terminology, the probability that someone is infected is called our prior, which is sort of our sort of intuitively speaking, the prior represents our belief in something before we see any extra data. So in this case, the prior, we just know that this disease occurs in 0.1% of the population. So the probability that a randomly chosen person is infected is 0.001. I believe that's 0.1%. And then what are the rest of these things? Let's compute them out real quick. So the probability that you get a positive test, given that you are infected, is, well, we said the test is 99.8% accurate, in the sense of 99.8% of infected people test positive. So this is 0.998. And then the probability of a positive test at all, sort of total, well, again, I don't want to write it out because these event names are rather a lot of ink. But again, we're going to break it down into the people who test positive and are infected, and the people who test positive and are not infected. So the infected people, they make up 0.001% of the population, and the probability that they test positive is 0.998. Uninfected people, on the other hand, make up 0.999 of the population, and the probability that they test positive is 0.002, which is 0.2%, which is the opposite of this. Or rather, the opposite of this, uninfected people testing negative. So now we've computed everything on this side, and Bayes' theorem allows us to compute this side. So the probability that someone is infected, given that they had a positive test. Another piece of terminology, this is what we call our posterior. So prior sort of means before we see extra data, what are our beliefs? And posterior means after we see this new data, namely the positive test, how does that change our beliefs? So the posterior is our updated beliefs based on new evidence. So in this case, let me not write out the whole formula, but we're just putting together, plugging in all these numbers, and what we get is if you test positive, the probability that you are infected is about 0.33, which is to say that a positive test, still, you are more likely than not to be uninfected. There's only about 1 in 3 chance that someone who tests positive is affected. And how can we interpret this? This is saying, one way of interpreting this is saying that even though the test is extremely accurate, the disease is so rare that a false positive is still going to be more common than a true positive. So a positive test, what is the probability that you're infected, is essentially trying to measure the amount of positive tests that are true positives versus false positives. And that very much fits in with the first interpretation of Bayes' theorem that we gave. But this, the interpretation that we're talking about right now is saying that we should not see this positive test and try to draw conclusions based on that alone. We should have some prior understanding of the situation, and we should use this test, which is some new evidence, to update our prior instead of making some guess out of thin air. So you can see that when we take into account this new evidence, the probability of being infected does go way, way up, but it still is less than 0.5. So it's still more likely that you don't have the disease. And just to emphasize, this really is how medical testing works. You know, this is well understood by doctors, and actually secretly I did get these numbers from a CDC document explaining basically this exact thing. So in reality, there are situations like this, and this is what you need to know in order to judge these situations. So a negative test, you can interpret that to mean that you're uninfected. We didn't calculate that right here, but that's another application of Bayes' theorem. If you want to go and check that yourself, if you test what is the probability that you're uninfected, given that you test negative, then you'll find that it's extremely high. On the other hand, a positive test, what does this mean? Well, we've seen that it's likely that you're still not infected. So you don't conclude that you're infected, you just say that more testing is required to find out what's really going on. So just to say a couple words about this philosophy, the idea is that Bayes' theorem tells you if you have some prior belief or hypothesis about the world, and you see some new evidence, then Bayes' theorem tells you how to update your beliefs based on this new evidence. So the philosophy, the Bayesian philosophy, is not to take evidence in a vacuum and just get blown around every time there's new data, nor to stick stubbornly to your beliefs and ignore all the new data, but to have your priors and use all the new data that you encounter to update your beliefs in a reasonable way. Now, there is some potential criticism of this philosophy, which is that it depends very much on having good priors. So, for example, in this medical testing example, we can already see this. Suppose a disease occurs in 0.1% of the population, but maybe this patient you know more things about. Maybe they're a member of a population that is at particularly high risk. Maybe they're from a place that has had an outbreak of this disease, and other factors, so that judging the prior can become a little bit subjective. And almost the whole point of Bayes' theorem is that the prior has a large impact on what your conclusions should be. So if you do not have a good estimate of the prior, that can really affect how good of an estimate Bayes' theorem gives you. So there is some philosophy, but in this realm, I will allow you to make your own judgments. But it is good to know examples like this to be able to understand how Bayes' theorem works and how to interpret it.